Hello friends, welcome to the class of high voltage engineering. So today I am going to discuss about the high voltage testing in various parts. In first part we are going to discuss about the important facts related to the high voltage testing, that why the high voltage testing has been performed over the high voltage equipments. In the next part, we will see the various types of testings which are broadly conducted over all the high voltage equipments. And in later on stages, we will discuss the different types of testings performed over the different types of equipments. So high voltage testing. So electrical insulation, as you all know that it is normally considered as a heart of the electrical engineering or the electrical power system network, or it can also be considered as a backbone of all modern power system networks. The electrical stresses normally affect the insulation's property, and as the life goes, its life expectancy gets reduced. So generally the electrical stresses experienced by the insulations effectively reduces its life expectancy over a longer time of its operation. So what it needs a thorough understanding of fundamental properties of insulating material and its failure mechanisms during the service is very essential for the appropriate and optimal design. So ideally, by conducting the high voltage testings over the insulating materials or over the high voltage equipments, the insulation engineer or the electrical engineer can come to know about its quality and what sort of the modification needs with the insulating material to obtain a very good performance. So in one sentence we can say that the conduction of the high voltage testing is very essential for obtaining the appropriate and optimal design of the insulating materials so that it can withstand the over voltage situations over a longer time. So ultimately the life expectancy of the high voltage equipment can be raised by conducting the high voltage testing so that the insulation engineer can create the appropriate and optimal design. So as a result, the high voltage insulation technology has undergone many changes, with advances being made in the area of testing, measurement and development of new materials. So these are the three verticals in which the electrical engineer or the insulation engineer can contribute. In our session, the testing is very important. So I'm going to touch upon the testing part only. I'm not going to deal with the measurement and the development of the new materials. So the testing plays a vital role in the electrical transmission network. So by learning this high voltage testing, one can design the optimal insulation for the high voltage equipment, which can allow the equipment to operate satisfactorily over its longer life of span. And for the purpose of this study, the high voltage laboratories have been developed. Sorry. So you know the various types of high voltage equipments, and yes, you have also seen in the switchyards or even in the power plants or during your field studies. Okay, so here I have categorized various types of high voltage equipments like the insulators, transformers, circuit breakers, isolators, lightning arresters, surge absorber, bushing, cable, and power capacitors. So in high voltage laboratories, the testings are normally conducted on all of the devices just to assure the quality of that product. So once the testing engineer assures the quality of that device or quality of that equipment, one can easily one can easily predict its life, and based on the quality of that equipment we can also judge the quality of our power system network. Okay, so let us see the different types of videos over the few of the equipment so that one can understand the importance of the high voltage testing. So let me first show the flashover of the high voltage insulators. So normally the high voltage testings which are performed on the insulators just to evaluate its quality, whether the line insulator is capable to withstand the over voltage magnitudes at power frequency or at the high frequency under the dry condition or wet condition. Okay, so this video will give the highlight over the high voltage test which is being performed on the insulator to evaluate its quality under the contamination condition.
The High Voltage Lab at Zittau University, Germany, tests the electrical resilience of insulators with and without PowerSil insulator coating. Uncoated porcelain insulators that are contaminated with a wet film layer are prone to electrical discharges, which can lead to flashovers. Such pollution layers can give rise to leakage currents and thus losses. In the worst-case scenario, they result in flashovers and power outages. Wacker's PowerSil insulator coating can be applied to both existing insulators and new ones yet to be installed. It reduces the risk of pollution flashovers, which increases reliability and efficiency. For the test, 2 insulators with and without coating are moistened with saltwater spray. During the spraying, the silicone's hydrophobic, that is to say water-repellent, properties become apparent. In direct comparison, insulators are exposed to a steadily increasing voltage. At an elevated voltage, the uncoated insulator starts to display partial discharges, which leads to a pollution flashover. The insulator coated with PowerSil insulator coating, on the other hand, still doesn't exhibit any electrical discharges. In order to simulate realistic environmental field conditions, an artificial pollution layer, which on an uncoated insulator would lead to a pollution flashover under real conditions, is applied to a coated insulator. Both the artificially contaminated coated insulator and the clean uncoated insulator are moistened with saltwater spray. Here, the silicone coating reveals its most important property, hydrophobicity transfer. The silicone's hydrophobic properties are imparted to the pollution layer. At an elevated voltage, the coated insulator does not lead to discharges despite the additional pollution layer, while the clean, uncoated insulator exhibits a pollution flashover. With PowerSil insulator coating, Wacker experts have developed an efficient, long-lasting solution that will revolutionize the performance capability and service life of insulators. Wacker.
So in this video you have seen the testing on the insulators with and without coating. Okay, so when the coating is not applied, you have observed the flashover across the insulator's body. Okay, so the insulation engineer has modified and coat the body of the insulator and again retested. Okay, so you have seen the effect of that coating. Okay, the silicone coating has been done over the insulator. Okay, so when there is a spray of the water particles and under the impact of the high voltage stress, there is no flashover has been observed because of that coating. Okay, so one can improve the design by applying the coating to the line insulators, so that you can avoid the chances of the flashover during the contaminated conditions. Let's come back to our PPT. So let us see the uh, world's biggest transformer, which has been developed by the Siemens.
Its dimensions are one of a kind. 37.5 meters long, 12 meters wide, and 14.4 meters high. The biggest transformer in the world. With it, Siemens enters new territory in surpassing the 1100 kilovolt limit. To achieve this feat, the engineers had to develop a valve lead system as well as the overall transformer design itself. The result is a giant step forward at a 55% increase of rated power of the single-phase transformer. These transformers feed into a transmission system at a voltage level of 1100 kilovolts direct current, transmitting electrical power of 12 gigawatts. To manufacture this giant, Siemens invested double million figures in its factories and testing facilities. Besides the technical challenges of breaching the 1100 kV hurdle, the engineers were presented with another trial: how to get a machine as big as a detached house to the inland port of Nuremberg. They had to adapt. Departure day. The Siemens 1100 kV begins its journey over more than 23,000 kilometers to its final destination, Guchuan in China. The first step is reaching Nuremberg Harbor. As early as the design stage, the Siemens experts included the limitations of the transport route into their plans. And these 7.4 kilometers will be the trickiest part of the whole journey. Finding the middle ground between maximizing the transformer and still fitting through the tightest passages. A masterful demonstration of engineering excellence. This task was never an easy one. Unforeseen challenges during this transport took their time, till the transformer reaches the harbor 8 hours after departure. From here, the 1100 kV travels first to Antwerp. After being loaded onto a cargo ship, it continues its voyage to the next harbor, the distant Shanghai, over 22,000 kilometers away. "51 days later, the Rickmersdalion ships into the port of Shanghai. On board, the Siemens 1100 kV. The next step of the journey is near. The transformer is lifted onto the barge, which will transport it to its final destination. The project is aiming at cities like Shanghai, energy for the growing population, and therefore rising energy demand in the coastal regions of China. Finally, the 1100 kV arrives, Guchuan substation in Anhui province. The transformer's position is at the receiving end of a record-setting HVDC connection, over 3,284 kilometers from the northwest of China to this station. One of the key factors for the success of projects like this, the Siemens network of factories. Throughout its production sites around the world, Siemens workers are highly skilled for building these transformers by hand. This high level of quality is made possible through technology transfer between Siemens headquarters in Nuremberg and all its factories and partners. When the project is completed, a total of 7 1100 kV transformers will supply the neighboring provinces with energy. Surely a milestone for Siemens. Thanks to the transformer factory in Nuremberg, the future looks bright.
So now let us see about the lightning arrestor.
Greetings, everyone. This is John Woodworth of ArrestorWorks. Today's discussion is titled, What is a Lightning Arrestor? Although a lightning rod does protect from lightning, it does so only on structures and is not an arrestor. Lightning rods are devices that divert lightning surges to ground, but unlike arrestors, they are simple, conductive terminals that are always at ground potential and are never energized. According to most definitions, a lightning arrestor is a device used on power systems above 1000 volts to protect other equipment insulation from being damaged by lightning and switching surges. The SPD and the TVSS are devices that are similar to lightning arrestors in that they are surge diverters, but they are generally used at voltages well below 1000 volts. So how does a lightning arrestor protect the power system? Let's take a look at an example where the transformer is not protected by an arrestor. If lightning were to strike the line, the current will flow down the line into the transformer. This action will most likely result in damage to the transformer and the lights will go out. However, if the transformer is protected by an arrestor and the line is hit by lightning, the arrestor will turn on and divert the surge to ground. The arrestor protects the transformer from damage and, of course, the lights stay on. So how does an arrestor work? Things it does not do is it does not absorb the lightning and it does not stop the lightning. It does, however, clamp or limit the voltage produced by the lightning, and it does divert the lightning current to ground. It should be noted that the arrestor will only protect equipment that is electrically in parallel with it. So how does the arrestor divert the lightning? To answer that, let's discuss the metal oxide varistor, or MOV disk as it is referred to. The MOV disk is a semiconductor that is sensitive to voltage. At normal voltages, the MOV disk is an insulator and will not conduct current. But at higher voltage caused by lightning, it becomes a good conductor. Essentially, the MOV disk is a very fast-acting electronic switch. It is an open switch to standard system AC voltages and a closed switch to lightning voltages. If we were to magnify the MOV material 5,000 times, we would be able to discern the metal oxide grains and dopants in the material. An MOV disc with a 35 millimeter diameter and a 35 millimeter height contains about 28 billion MOV grains. A lightning arrestor is basically a collection of billions of microscopic junctions of metal oxide grains that turn on and off in microseconds to form a current path from the top terminal to the ground terminal of the arrestor. This action prevents the voltage from overstressing the equipment it is protecting. So there you have it. A lightning arrestor is a device used in power systems. It contains billions of electronic switches, and during a lightning strike, it diverts lightning currents around sensitive equipment and saves their insulation from damage. We hope this arrestor facts has provided a better understanding of what an arrestor is. As always, we welcome any feedback or questions you may have. Remember, ArrestorWorks.com is your surge protection resource center for power systems. And have a great day.
So this is about the few of the equipments Likewise, you can also search out on the YouTube for the other equipments just to understand that how they are operated. Now let us have the one kind of the virtual visit to the high voltage laboratories. So in the first video I am going to represent about the architecture of the world's largest high voltage laboratory, which is available into the Spain, and into the second video I will going to demonstrate virtually about the Electrical Research and Development Association, which is one of the high voltage laboratory located in Gujarat, Vadodara. So let me play the first video just to understand the architecture of the high voltage laboratory. Yes, this will show the three-stage cascade transformer, and over the top the high voltage electrode is generally electrostatically shielded. Okay, so shielding is very much important when you are playing with the high voltages, just to avoid the surrounding air to become ionized. So in this you can see the arrangement of the high voltage laboratory. In the first phase you have seen that the three transformers are normally connected in series to produce the very high magnitude of voltage. Okay, on to the right hand side you can see the triggering gap for the impulse voltage generator. Okay, so the first side the cascade transformer for the purpose of generating the very huge amount of voltages. Then of course the measurement is required, so ideally the resistive potential divider circuit is used. Okay, and at the later on stage you will see the charging of that impulse voltage generator. Okay, so in the case of the high voltage laboratories, the most important equipments that the people can attract it are the cascade transformers, impulse voltage generators, and so on. So engineer has performed the impulse voltage test on the test equipment. So you have noticed that the waveform has been captured onto the screen of the computer, from where the testing engineer can analyze whether any kind of defect has been occurred when the impulse voltage test was being performed. Okay, so ideally when we are performing the impulse voltage test, the three different types of impulse voltage waveforms can be captured. One is the full impulse, which notifies that the insulation of the equipment is capable to withstand the applied impulse voltage magnitude. Second is the oscillatory impulse, and that oscillatory impulse notifies the internal defects with the insulation, and if the chopped impulse is there, then the insulation is very poor and not capable enough to withstand the applied impulse voltages. So this kind of the judgment or decision can be taken by analyzing the captured wave shape. So when you are performing the impulse voltage test, you need to capture those impulses by using this DSO, so potential divider circuit, along with the CRO. So the output is normally given to the laptop or the computer on which you can capture the wave shape and analyze it to reach to the decision. So now let us see the virtual tour of Electrical Research and Development Association, ERDA, which is located at Vadodara in Gujarat.
Electrical Research and Development Association, ERDA, is a premier laboratory in India for testing, calibration, certification, consultancy, as well as research and development of electrical products. ERDA was established in 1974 at Vadodara, Gujarat, with the support from the Government of Gujarat, Government of India, Electrical Industries and Utilities. ERDA is a not-for-profit organization registered under the Societies Act and as a charitable trust, Mumbai Act. We are also exempted from income tax. The main complex is at Vadodara and regional laboratories across India. ERDA caters to more than 5,000 domestic and international customers. ERDA is accredited by NABL, Intertech Aster, TUV-PS, Germany, BIS, BEE, and recognized as a CSIRO by DST, Government of India. It is also recognized by utilities, PSUs and several other agencies. ERDA is an ISO 17025 certified laboratory. The quality of the transformers can be ascertained by routine, type and special tests. ERDA has 3 state-of-the-art short-circuit test stations for power and distribution transformers. We have India's largest online short-circuit station, which can test short-circuit withstand capabilities up to 4 MVA, 33 kV class power transformers. ERDA has 3 impulse laboratories with maximum capacity of 1600 kV peak, 80 kilojoules. The sophisticated impulse test laboratory conducts lightning impulse and switching impulse test on power, distribution and special types of transformers up to 100 MVA 400 kV class. Test capabilities are available for conducting temperature rise test on distribution transformers up to 2 MVA 33 kV rating at laboratory and up to 100 MVA 220 kV rating at manufacturer's end. ERDA conducts routine and acceptance tests on distribution transformers up to 2000 kVA 33 kV at laboratory and up to 100 MVA 220 kV at location. Routine and acceptance tests include load loss and no load loss, vector group checking, winding resistance measurement, turns ratio, and insulation resistance measurement. We also evaluate star ratings of transformers according to BEE guidelines. Other special tests like noise level, harmonics, zero-phase sequence measurement, and pressure test on transformers are conducted according to national and international standards as well as CBIP guidelines. The reliability and performance of the transformer depends on the quality of materials used. The major materials are the winding, core, and insulating materials. ERDA has an advanced facility for evaluation of materials used in transformers. The CRGO laboratory is the first to be recognized by BIS for carrying out tests on single-sheet CRGO laminations as per standards. Copper and aluminum conductors of transformers are regularly evaluated here. ERDA tests a variety of solid insulating materials such as papers, press boards and tapes. We have sophisticated instruments for evaluation of insulating materials. The tests include dielectric strength, cracking index, dissipation factor, and physical properties, as well as various aging tests. Our decades of experience in testing and interpretation of dissolved gas analysis and Furan analysis of transformer oils has resulted in prevention of many potential failures by timely diagnosis. All transformer accessories like bushings, Buchholz relays, radiators and tap changers are also evaluated as per IS-IEC standards. ERDA has complete infrastructure and competence to evaluate the health index of transformers in service by conducting capacitance and tan delta measurements, partial discharge measurements, SFRA DGA, and dielectric response analysis. With a rich experience in testing, we have completed various R&D projects on transformers. One of the major achievements has been the development of the online fault sensor. Our analytical center is equipped to undertake various electromagnetic, structural, and thermal analysis of transformers. The inspection wing of ERDA carries out third-party inspection of transformers and accessories on behalf of utilities. Over the years, ERDA has been consistently serving the transformer industry and utilities by providing timely and accurate test results. We are committed to provide quality services by continuous augmentation of our facilities as per emerging technology trends.
So this is all about the ERDA. So now let us see the types of testing. So normally the testings on the high voltage equipments or the insulation broadly classified into the two categories. One is known as a destructive testing and second is known as a non-destructive testing. So the name itself suggests the definition of the two types of these testings. So destructive testing, it means that all the high voltage testings are normally put up into the category of destructive test, because while we are performing the high voltage test, there might be the situation that the insulation may get collapsed. So whatever the test that we are going to perform on the high voltage devices can create the damaging effect, then that test is known to be the destructive test. Whereas in case of the non-destructive testing, the testing engineer has to take care of that the insulation should not be damaged permanently. Okay, so like the partial discharge test and the tan delta test normally put up into the category of the non-destructive testing, because the voltage that is being applied during these testings are not capable enough to create any permanent damage to the insulation. So these are the two types of the testings which you can usually see with the see in the high voltage laboratory. One is the destructive test and second is the non-destructive testing. So non-destructive test, as I said, the material is not being destroyed. It can be done to assess the electrical properties like DC resistivity, dielectric constant, dielectric loss, okay, then dielectric loss factor over a wide range of the frequencies. In high voltage equipments, the quality of the insulation can be assessed by measuring the loss factor at high voltage and also by conducting the partial discharge test. So partial discharge test can also be put up into the category of non-destructive testing. So non-destructive test includes DC resistivity test. It is generally being performed to determine the resistivity of an insulation, which is one of the electrical property normally associated with all dielectric materials. Tan delta or dissipation factor measurement test. So high voltage shearing bridge is used where the dissipation factor or the loss tangent can be determined at low frequency, power frequency and the audio frequency ranges. So that test is normally performed to determine the dielectric loss, dielectric constant and the loss tangent, that is the tan delta. Partial discharge test is performed to detect any deterioration or the faults being present in the internal structure of the insulation of the equipment. The destructive testing, high voltage test, because ultimately when the huge amount of voltage is being applied to the dielectric material, obviously it may create damaging effect. So basically the low voltage tests are normally put up into the category of the non-destructive test, whereas the higher voltage tests normally put up into the category of destructive testing. So high voltage test on the electrical equipments are carried out by the following procedure provided by the standards. If you have seen in the video that they are talking about the IEC and IS and the other standards. So the testing engineer, while he or she is working in the high voltage laboratory, he or she has to follow the rules and regulations and the guidelines, procedures and everything as per the standards suggestions. So the standards which are normally adopted by the high voltage laboratories to perform the high voltage test are the IEC, International Electrotechnical Commission, IS, Indian Standard, BS, British Standard, AS, American Standard, NEMA, NEMA, that is National Electrical Manufacturers Association, and IEEE, Institute of Electrical and Electronics Engineers. So normally the Indian industries follows IEC standard, IS standard, NEMA standard and IEEE standard. So if we are considering the manufacturing industries, then they has to follow the guideline of NEMA. Okay, but when it comes to the high voltage laboratory, except this NEMA standard, the other standards can be applicable. So if the high voltage laboratory is assigned a task to test the high voltage equipment which needs to be installed in the United Kingdom, then the testing should follow the process of the British standard. So we cannot use the guideline of this IS. So if suppose the laboratory does not have the British standard, then the laboratory person can follow the procedure of IEC, International Electrotechnical Commission. So let us see the high voltage laboratories in India apart from the ERDA. So one you can see at BHEL, Bharat Heavy Electricals Limited at Bhopal. One is at CPRI, Central Power Research Institute, Bangalore. Yes, of course, you found the high voltage laboratory in Indian Institute of Science, Bangalore. Then in IIT Madras. Okay, then Government Engineering College, Jabalpur, Anna University, Madras, Jadavpur University, Kolkata, Engineering College, Jawaharlal Nehru Technological University. Okay, then Central Power Research Institute's Ultra High Voltage Laboratory at Hyderabad. So into the table you can see the indoor test facilities as well as the outdoor test facilities with with the different voltage scales. So normally the highest voltage level of the high voltage laboratories can be specified based on the impulse voltage value level. So when you are visiting any of the high voltage laboratory, this simple principal circuit you can analyze. So first you can see the power supply, which is regulator, because if we are considering the electricity board of the India, then the voltage that we are getting is single phase or three phase. So single phase, if we are considering, then it is 240 volt or 230 volt, and three phase of 11 kilovolt. Okay, so 415 volt to 11 kV. So maximum amount of voltage is normally preferable to select, because if you are going with the very large magnitude of voltage, then you can imagine the cost of developing the high voltage laboratory. And apart from that, you need to take care of the severe conditions as well. So generally the voltage regulators are use step up transformers, which can step up the voltage level from 415 volt or 11 kV, from 11 kV volt to 220 kV for the testing purpose. So first initially you can see the power supply regulator, just to obtain the proper value of the voltage for the testing purpose. Okay, so generator, here generator, that is not the rotating generator, it is the testing transformer or the step up transformer, which can produce the very large magnitude of voltage. So that generator may be the maybe a single stage of testing transformer, or it may be the cascade transformer, it may be the voltage multiplier circuit, it may be the impulse voltage generator, it may be impulse current generator. Any kind of generating technique, you can consider it as a high voltage generator. Afterwards, the testing object is placed, and that testing object may be of the lightning arrestor, circuit breaker, transformers, insulators, bushings. Okay, the quality assurance can be done by measuring the various parameters. So to measure that parameters, the voltage divider circuits are normally connected with the test setup. So this voltage divider may be of resistive type, capacitive type, or even a combination. Okay, then coupling capacitor, if one is performing the test under the DC stresses, then we need to remove the ripples. Okay, so to remove those ripples, the coupling capacitors are normally utilized just to remove the harmonic content from the produced DC voltage. The coupling capacitors can also be found during the partial discharge test as well. Okay, so afterwards you will have the software technologies, from where indirectly you can assess the quality of the insulation during the conduction of the test. So this is the very basic circuit arrangement usually you can see in any of the high voltage laboratories. So let us quickly see some photographs related to the equipments that you see in the high voltage laboratory. So here you can see this is the three-stage cascade transformer, which has a voltage level of 1000 kilovolt. This is the DC test voltage setup up to 1500 kV. This is lightning or switching impulse test voltage facility up to voltage level of 2400 kilovolt. This is artificial rain test setup to test the insulators of 800 kilovolt. Okay, this is the arrangement to conduct the impulse voltage test on transformer. This is corona cage for the corona studies. This is the high voltage test laboratory available at TBEA at CPRI Hyderabad outdoor. Okay, apart from this hardware setups, you can also found some of the simulation softwares which can give the broader kind of exposure to the insulation engineers to create the optimal design of the insulation. So like the ProE, Quickfield, Magnet, SolidWorks, ANSYS, FEMM, then the MATLAB. The virtual high voltage laboratory is a one kind of the study tool by which the students can learn the high voltage testing from their home as well. So this is about a simple introductory session towards the high voltage testing, about its importance and the high voltage laboratories. In the next part of this session, I am going to discuss about the various types of testings which are conducted. Okay, and then we will see the circuit breaker testing, transformer testing, insulator testing, and so on. Thank you.